Okay, so hey everybody, this is Mr. Bells again. We're going to talk about Geometry A, Section 2-2, and things called conjectures, and inductive reasoning, deductive reasoning, the difference between the two of those things, and then we're going to talk about a counterexample and some laws of logic. So, we're going to start off with this right here, and hopefully this can be nice and bright enough for you. So the first thing that we want to talk about is a conjecture. So a conjecture is kind of like in science a hypothesis. It's an educated guess. It's something like, man, I think that's probably true. Okay, so for instance, you walk outside, you look at the sky, and you're like, holy crap, it's dark out. Overcast, looks like storm clouds, and you think, conjecture, boy, it's going to rain. Okay, that is a pretty good sign of it. That's something that you're guessing. If I'm playing baseball or softball, one of the things that I would talk about some of the times is, man, I think this is what this team's going to do, and if that's what I think they're going to do, then I'm going to prepare for it, and that's conjecture. Now, in a conjecture, there are two different types of reasoning that we can look at right now. One of them is called inductive. And that's where you base your conjecture, base it on observations, or patterns. You don't necessarily know that it's true, but you really believe that it's going to be true. Whereas deductive is based on facts or laws, things that are given to be true. Okay, so when we're talking, give me an example of inductive. Then we're when I'm playing in a baseball game, I'm up there to bat, and I notice that in the first inning, when the pitcher got in an 0-2 count, which is no balls and 2 strikes, and if they get 3 strikes, then the batter's out. When they're in 0-2 count, they throw a slider away from the batter. Okay, in the third inning, it happened again on an 0-2 count, threw a slider away. So me, using a little logic, if I'm standing up there to bat, and they have 2 strikes on me, I'm thinking to myself, this seems to be what their go-to pitch is. I'm going to use something called inductive reasoning. Based on the patterns that I've established before in the game, I'm going to think slider away. And maybe I'm going to adjust to it, okay? Maybe that means I'm going to crowd the plate a little bit more, I'm going to reach out for the slider, or maybe I just know that it's going to be away and I'm going to lay off of it, okay? Now, I don't know that it's true. It's not a fact. I didn't turn around and see the catcher splash him 2 for a curveball or slider and point to his outside leg away from me. I don't know what it is, but based on my observations, that's called inductive reasoning. Deductive reasoning would be if we knew the signs of the other team, and we've already established and we've seen what the signs are, and I'm like, yes, I know what this pitch is going to be, and we might have to talk to the Houston Astros about that. If you don't know what that reference is, you can Google it, but we can Google anything right now. But that would be deductive. Last year, when we were in school, I might have gone down to the cafeteria on a Friday or two and noticed that they were serving something called chicken bowl, which is mashed potatoes, corn, and gravy, and a little popcorn chicken. And it's, oh, that's really good. And maybe it happened 3 Fridays in a row, and I'm like, hey, inductive reasoning goes, man, they have this a lot on Fridays, maybe they'll have it again on the next Friday. Now, if I was to use deductive reasoning, then I could actually look at their menu beforehand, and I know that, yes, they do serve chicken bowl every Friday. Okay? So are we good on the difference between inductive reasoning and deductive reasoning? Good deal? Okay. So what's next? So lots of times when we're talking about making conjectures, we believe that something might be true. So here's my conjecture. my conjecture. If I square a number, it gets bigger. Awesome, right? It gets bigger than what it was. So that's my conjecture. So then I'm going to go, let's test that conjecture. Let's take the number 5 and let's compare it. So 5 compared to when I square 5, that's 25. Did indeed it get bigger? Like, yes. Okay. Does that mean my conjecture is true? No. That means a specific case of my conjecture was true, but I don't know that it's completely true. So I'll try another one, like 10. Awesome. So 10 squared becomes 100. Did it get bigger? And you're like, yes, that must be true now, right? No. Just because it works twice doesn't mean that it works forever. So then I try another one. Let's try 1. And 1 squared, right? When I'm talking about squared, we're talking about comparing x to x squared. 1 squared is actually 1. Did it get any bigger? The answer is no. Okay? So in that case, this would be something called a counter example. And that's one word, but I don't want to run out of space for you guys to be able to see it. So that'd be a counter example. Everybody good with that? Good deal? Okay. Now, so what I could do is I could now reassess my conjecture and tweak it a little bit and say, well, what if I say if I square a number, it gets bigger or equal to itself? Then that conjecture is still true, right? And even if I tried 0, like 0 squared is still 0, and you're like, bam, I'm still good. Like all 4 of these things work. I'm like, try some negatives. So -7, and if I square a -7, remember you got to put that in parentheses, right? If you put it in your calculator, because -7 squared means -7 times -7, which is 49. And like, did that get bigger? And you're like, yes. So it works for positive, it works for 1, it works for 0, it works for negative. It's like, that must be true, right? Right? Unless somebody out there thinks that they've got a counterexample. And if you do, that's awesome, because there is. So, pause the video right now, just in case you think about what might a counterexample be for this. And if you don't know, that's okay. Think about it. I'm going to tell you what it is in about 3 seconds. 3, 2, 1. Awesome. So one of the key numbers we haven't looked at is a fraction. So if I take 1/4 and I square it, which is 1/4 times 1/4, then that ends up being 1/16. And in this case, this product doesn't give me something that's bigger. Okay? So this is another counterexample to my new conjecture up there, which means that that conjecture wasn't true. Okay? Feeling pretty good about that? So, so far we've talked about what a conjecture is, just a logical, educated guess, using inductive or deductive reasoning based on observations or pattern that was established as inductive, based on things that you know are true facts, laws. And later on throughout this course, we're going to talk about something called a proof. And a proof always uses deductive logic, means things that we have to know are true, factual things. And then we just talked about what a counterexample is. So last thing right now in this section, I think that blue is showing up okay for you. I'll pop this back a little bit so you can see here. And this is called laws of logic. So laws of logic. And there are 2 main laws of logic. One of them is called the law of attachment. And the law of attachment basically says this, that if P implies Q is true, okay, this has got to be a true statement, so you can't make stuff up. This has to be true. And P happens, if this actually does occur, then Q also happens. Right? So, here's a statement. If I get a job at Olive Garden, which one of my twins just did, then she's going to make some pretty good money at tips. Okay? She's going to do that. So, if she indeed actually does get a job at Olive Garden, then this has to happen, right? Okay, if the original statement was true. Now, it could be, right? It could be that she got a job at Olive Garden as a manager, or as a cook, or as a busboy, and maybe they don't get tipped out. Maybe they do. I don't. Some restaurants they do, some restaurants they don't. But I'm only assuming that this is true, and if that's true, then the law of detachment says if P happens, then Q also happens, which means I can't detach, I can't break that apart. If the first thing happens, it's guaranteeing the second part, okay? And then there's something called, and this one's kind of weird sounding, syllogism. Law of syllogism basically says this: if P implies Q is true, and Q implies R is true, and these P's and Q's and R's are just random letters to represent something, then the law of syllogism says that I can go all the way to here, that I can kind of snake through those statements, okay? And there's a great song out there that I've played in class before. Maybe I'll do it for you guys in my time, called Third Rock from the Sun. And basically it's like a chain of events, right? If this, then this is true, and if this, then this is true, then what happens? So let's say that, we'll go back to that cleaning the room thing. So if I clean my room, P, then I get to go out Friday night. Q, true, awesome. If I go out Friday night, then I'm gonna run into some of my friends, right? If let's go another level here, we can go another level here. R implies T. If I run into some of my friends, then I'm gonna have a good time. Good deal? So all those things happen. So basically, the law of syllogism says I can sneak through all these ones and basically say, if I do clean my room, then I'm going to end up having a good time Friday night. Good deal? Okay, so those are the conjecture, inductive reasoning, deductive reasoning, counterexample, and laws of logic, the two laws that we have, detachment and syllogism. Hopefully this was beneficial to you. We will talk to you guys later.